I'm so pleased you're here for tonight's quiet journey into one of the strangest places in the universe, the inside of a black hole. Just a little favour to ask before we begin. As I'm sure most of you know, there are no ads on these videos, so nothing will distract you tonight. If you have a moment to spare, I'd really appreciate it if you took a look at our ebook over on the Sleepy Scientist website. It takes the ideas from these videos and gives them room on the page, unhurried, laid out with all the space they need to properly settle in the mind. The whole thing is narrated too, so you can read it or simply listen. And at the close of each movement there's a short quiz waiting, a gentle way to see what stayed with you and to turn the ideas over once more before moving on. The QR code is up on screen, and there's a link in the description to the sleepyscientist.com whenever you're ready. Every reader who takes a look is the reason these videos keep appearing, and to anyone who takes the time to buy it, I don't think you quite understand how much that means. That's the only ask tonight, and thank you sincerely. Now, before we drift too far in, let me know where in the world you're listening from and what time it is for you. I always enjoy seeing these little check-ins from around the world as people settle in for the night or the morning or the middle of an afternoon that has somehow become black hole shaped. Tonight we're asking not just what a black hole looks like from the outside, or why light cannot escape, but what might happen once something crosses the event horizon and passes beyond the reach of the rest of the universe. It's one of those questions that feels almost too big to hold in the mind at once, so we'll take it gently. We'll begin with the familiar idea of gravity, then follow it into Einstein's curved space-time, through the event horizon, into the strange inward direction of the black hole interior, and finally towards the limits of what modern physics can honestly say. Along the way, we'll meet some of the deepest ideas in science: tidal forces, singularities, spinning black holes, Hawking radiation, entropy, quantum information, and the strange possibility that black holes may not simply be dark endings, but clues to a deeper theory of reality. So get comfortable, let the day loosen its grip a little, and allow your thoughts to slow down. Tonight, we're not travelling outward to the edge of the universe, we're falling inward, towards the place where light cannot return, where time and space become strange, and where black holes quietly show us the edge of physics itself. What happens inside a black hole is one of the strangest questions in modern science, because it asks us to look into a place that, by its very nature, cannot send anything back. A black hole is not simply a dark object floating in space. It is a region where gravity has become so intense that the usual routes of escape have closed. Light cannot climb out. Matter cannot turn around and return. Signals cannot be sent back to the outside universe. Even ordinary intuition, which works quite nicely for cups of tea, falling leaves and mildly disappointing weather, begins to fail. The inside of a black hole is one of the most extreme regions predicted by modern physics. It is where gravity is no longer just something that pulls objects together, but something that reshapes the structure of space and time. It is where the future itself seems to point inward. And it is where some of the deepest ideas in science, including general relativity, quantum mechanics, thermodynamics and information, all begin to press against one another. So the question is not simply, what is hidden inside a black patch in the sky? It is much richer than that. It asks what happens to matter after it crosses the event horizon, the boundary beyond which escape becomes impossible. It asks what happens to light when every possible outward path has been bent inward. It asks what happens to time when clocks near the black hole no longer agree with clocks far away. It asks what happens to space when directions no longer behave the way we expect. And it asks what happens to information, detailed physical description of everything that falls in. That last question may sound abstract, but it is one of the most important. If a book falls into a black hole, the outside universe may lose access to the words on its pages. But physics asks something deeper. Does the information that distinguished that book from a lump of coal, a cloud of gas, or a very unfortunate sandwich truly vanish? Or is it somehow preserved in a form we do not yet fully understand? Already the black hole has taken us far beyond the simple idea of a cosmic drain. There are parts of this story that science understands with great confidence. We know that black holes behave as real astrophysical objects. We know that extremely compact masses can bend light, accelerate nearby stars, heat surrounding gas, and merge in ways that produce gravitational waves. We know that the event horizon, or something behaving extremely much like it, is a central feature of the black holes described by general relativity. But there are also parts of the story where our confidence becomes more careful. The deep interior of a black hole leads toward what classical general relativity calls a singularity, a place where the mathematics predicts that density and space-time curvature become infinite. In physics, an infinity is often not a comfortable answer. It is more like a flashing warning sign saying that the theory has been pushed beyond where it can safely guide us. The true nature of that singularity remains unknown. Most physicists do not expect a complete answer to come from general relativity alone, because general relativity describes gravity and space-time, but it does not include quantum mechanics in a complete way. Near the smallest possible scales, where curvature may become unimaginably intense, many scientists expect that a theory of quantum gravity is needed, but a fully confirmed theory of quantum gravity does not yet exist. So from the very beginning, the answer has layers. Near the outside of a black hole, our theories and observations are strong. At the event horizon, general relativity gives a powerful and precise description. Deep inside, near the predicted singularity, we enter a region where our best existing theory tells us that it is no longer enough. That is not a failure of science. It is one of the most interesting things science can discover, a clear edge to what is known. Black holes themselves are no longer just hypothetical curiosities. They are supported by several major lines of evidence. The Event Horizon Telescope, a global network of radio observatories working together like an Earth-sized telescope, has produced images of the shadow regions around the supermassive black holes in Messier 87 and at the centre of our own Milky Way. These images do not show the event horizon as a solid surface. Instead, they show glowing material and bent light around a dark central region, just where general relativity predicts light should be captured. The Laser Interferometer Gravitational Wave Observatory has detected gravitational waves from black holes merging. These are ripples in space-time itself, produced when massive compact objects spiral together and collide. The first detection, announced after the signal observed in 2015, matched the predictions of general relativity with remarkable precision. It was as if space-time had been struck like a bell, and for the first time, humanity had built ears sensitive enough to hear it. At the centre of the Milky Way, long-term observations of stars orbiting Sagittarius A star have given another powerful line of evidence. Astronomers, including Andrea Ghez and Reinhard Genzel, along with their research teams, tracked stars moving around an unseen object with about 4 million times the mass of the Sun. These stars travel along tight, fast orbits around something incredibly compact. The best explanation is a supermassive black hole. The theory behind all of this begins with Albert Einstein's general theory of relativity, completed in 1915. In this theory, gravity is not treated as an ordinary force pulling across empty space. Instead, mass and energy curve space-time, and objects move along paths shaped by that curvature. This was a complete change in the meaning of gravity. Einstein did not originally set out to populate the universe with black holes. In fact, the idea that nature might create such extreme objects was not immediately accepted. The mathematics arrived before the astronomical confidence. In 1916, Carl Schwarzschild found the first exact black hole-related solution to Einstein's field equations. He was solving the equations for the spacetime around a spherical mass, and hidden in that solution was a remarkable boundary. If enough mass were compressed inside a small enough radius, there would be a region from which not even light could escape. Today, that radius is called the Schwarzschild radius. For an object with the mass of the Sun, the Schwarzschild radius is only about 3 kilometers. The actual Sun is about 1.4 million kilometers across, so it is nowhere near compact enough to be a black hole. But the comparison gives a useful sense of the extremity. A black hole is what happens when mass is packed so tightly that space-time closes around it. That is the calm starting point for the journey inward. Some things are firmly grounded. Black holes exist. They curve space-time. They have event horizons, and they affect the outside universe in measurable ways. Other things are careful extrapolations from powerful theories. What an observer experiences inside, what happens near the singularity, and whether quantum gravity changes the ending entirely. To understand the inside of a black hole, the first step is to understand that gravity itself must change meaning. It is not enough to picture a stronger and stronger pull, like an invisible hand dragging everything downward. A black hole is not merely a place where gravity pulls harder than usual. It is a place where space-time is curved so deeply that the possible paths through reality are rearranged. Before anything can truly fall inside, gravity must stop being just a force in our imagination and become what Einstein showed it to be, the shape of space-time itself. To understand what happens inside a black hole, we have to begin with a deceptively simple question. What is gravity? For most of everyday life, gravity seems easy enough to recognize. It is the thing that keeps your feet on the ground. It is the reason a dropped spoon falls downward instead of hovering politely in mid-air. It is the reason Earth holds an atmosphere. The moon circles Earth, and Earth circles the Sun. Gravity is so familiar that it can almost feel obvious. Isaac Newton gave this familiar feeling a precise mathematical form. In Newton's picture, gravity is a force between masses. Every object with mass attracts every other object with mass. The larger the masses, the stronger the attraction. The farther apart they are, the weaker the attraction becomes. This view was astonishingly successful and still is. It explains falling objects, the paths of cannonballs, the motion of planets, the rise and fall of tides, and the return of comets after long journeys through the solar system. Newton's gravity is one of the great achievements in the history of science. It turned the heavens and the earth into one connected system. The same rule that describes an apple falling from a tree also helps describe the moon falling endlessly around Earth in its orbit. That was a remarkable unification. The universe became, in a sense, readable. And for most purposes, Newton's picture still works beautifully. If you're calculating the motion of a satellite, the path of a spacecraft, or the orbit of a planet, Newtonian gravity often gives answers that are accurate enough to be incredibly useful. It is not some discarded old idea, left in a dusty cupboard with questionable medical advice and hats from the 17th century. It is a powerful approximation. But black holes are not ordinary situations. They are not gentle tides, falling apples, or planets moving through the calm suburbs of gravity. They are places where mass has been compressed so intensely that Newton's view is no longer deep enough. The idea of gravity as a force pulling across space begins to miss the most important part of the story. This is where Albert Einstein changed the meaning of gravity. In General Relativity, completed in 1915, gravity is not treated as an invisible pull travelling through space. Instead, Gravity is the curvature of space-time caused by mass and energy. This is one of the most important shifts in all of physics. Einstein did not merely improve Newton's theory in the way someone might improve a clock by making it tick more accurately. He changed the picture of what the clock was sitting in. To understand that shift, we need to understand space-time. Space is where things are. Time is when things happen. In ordinary life, they feel separate. You can walk across a room, and you can wait for a kettle to boil, and these seem like different kinds of experience. But relativity shows that space and time are woven together into a single structure called space-time. Different observers can measure distances and durations differently depending on their motion and their gravitational environment, but those measurements are not random. They are different views of the same underlying space-time. Space-time is not a material fabric in the literal sense. It is not made of threads, rubber, or cosmic bedsheets, despite how often it is drawn that way. Those images can be helpful, but they are only analogies. Space-time is the mathematical structure that tells objects how distances, times, motion, and causality fit together. In Einstein's theory, mass and energy shape that structure. A star, a planet, or a black hole changes the geometry around it. Objects then move through that curved geometry along the natural paths available to them. What we call gravity is, in this deeper view, the result of objects following the shape of space-time. This is why Earth orbits the Sun. In Newton's picture, the Sun pulls Earth inward, while Earth's sideways motion keeps it from falling straight in. That description works extremely well. But in Einstein's picture, the Sun curves space-time, and Earth follows a natural path through that curvature. The orbit is not caused by a rope-like force tugging across empty space. It is motion through a curved geometry. These natural paths are called geodesics. A geodesic is the straightest possible path through a curved space, or curved space-time. On a flat surface, the straightest path is just a straight line. On the surface of a sphere, the straightest path is part of a great circle, like the routes aircraft often take across Earth. In curved space-time, free-falling objects follow geodesics. They are not being pushed along by engines or held up by a surface. They are moving naturally. This leads to one of Einstein's most powerful ideas, the equivalence principle. The equivalence principle says, in simple terms, that being in free fall under gravity is locally equivalent to being weightless far from gravity. Imagine an astronaut orbiting Earth. The astronaut is not outside Earth's gravity. Earth's gravity is still strong enough to keep the spacecraft circling the planet. But the astronaut, the spacecraft, and everything inside are all falling together. Because they are following similar paths through space-time, the astronaut floats. The same basic idea applies to someone falling toward a black hole. If they are falling freely, they do not feel gravity as an ordinary force pulling on every part of them equally. For a small enough region and a short enough time, they feel weightless. Their body, their watch, and any loose object beside them are all following natural paths through curved space-time. This is why the event horizon of a large black hole is not necessarily a place where a falling observer feels an instant jolt. The observer may cross it without any local sign that a boundary has been passed. Their own clock keeps ticking. Their own body continues along its path. The black hole has not suddenly placed a surface in front of them. Instead, the geometry of space-time has quietly changed what futures are possible. John Archibald Wheeler expressed the central idea of general relativity in a famous way. In paraphrase, matter tells space-time how to curve, and curved space-time tells matter how to move. That simple statement carries the whole rhythm of the theory. Mass and energy shape geometry. Geometry guides motion. A black hole forms when that geometry becomes extreme. If enough mass is compressed into a small enough region, space-time curves so strongly that an event horizon appears. The event horizon is the boundary beyond which no signal can escape to the outside universe. It is not a wall. It is not a surface made of matter. It is a boundary in the possible directions the future can take. For a simple black hole that does not rotate and has no electric charge, this boundary is described by the Schwarzschild radius. The Schwarzschild radius is the radius of the event horizon for a non-rotating, uncharged black hole. It is named after Carl Schwarzschild, who found the first exact solution to Einstein's field equations in 1916. The Schwarzschild radius depends on the mass of the object. More mass means a larger event horizon. If the Sun were somehow compressed into a black hole without changing its mass, its Schwarzschild radius would be about 3 kilometers. The actual Sun is about 1.4 million kilometers across, so this would require an almost unimaginable compression. If Earth were compressed into a black hole, its Schwarzschild radius would be less than a centimeter, roughly the size of a small marble. Earth is in no danger of doing this, which is reassuring for anyone with plans this week. The equation can be stated in words like this. The Schwarzschild radius equals 2 times Newton's gravitational constant times the mass, divided by the speed of light squared. That equation tells us something profound. A black hole is not created because matter becomes magical. It is created because enough mass is placed inside a small enough radius that the geometry of space-time closes around it. Once that happens, the event horizon marks the region where outward escape is no longer part of the future. Outside the event horizon, there are still paths that lead away. A rocket could fire its engines. Light could travel outward. Matter could, at least in principle, avoid falling in. But inside the event horizon, the situation changes. All future-directed paths lead inward. This does not mean everything is pulled inward in the ordinary Newtonian sense. It means the geometry of space-time has become arranged so that inward is the direction of the future. This is the essential change we need before asking what happens inside a black hole. Gravity is not simply a stronger and stronger pull, it is the shape of space-time itself. A black hole is what happens when that shape becomes so extreme that escape is no longer physically available. Once gravity is understood as geometry, the event horizon becomes far stranger than a surface. It is not a shell waiting to be crossed with a dramatic bump. It is the boundary where the possible paths through space-time stop, including any route back out. The black hole does not need to grab light like a hand closing around it. Beyond the horizon, even light's future points inward. The event horizon is one of the most misunderstood ideas in all of black hole physics, partly because the name makes it sound like a place you could point to and touch. It sounds like a surface. It sounds like the edge of something. It is very easy to imagine a black sphere hanging in space, with a sharp boundary around it, almost like a cosmic shell. Outside the shell, the universe continues as normal. Inside the shell, everything becomes mysterious and doomed. It is a tidy picture, and human minds do enjoy tidy pictures. But the event horizon is not a hard surface. It is not a glowing membrane. It is not a wall made of dark matter. It is not a glassy black skin wrapped around the black hole. If you crossed it, there would be no physical layer to break through, no sudden impact, no dramatic ripple spreading across a surface. The event horizon is not made of stuff. It is made of causal structure. The event horizon is the boundary around a black hole beyond which light, matter, and information cannot escape to the outside universe. It marks the point where outward communication becomes impossible. Something inside the event horizon can still have things happen to it. It can still move locally. It can still experience time along its own path, but it cannot send a signal back to distant observers outside the black hole. This is what makes the horizon so different from an ordinary border. A country border can be crossed in both directions. A wall can be climbed if you have enough determination, enough equipment, or a deeply unreasonable amount of confidence. But the event horizon is not a barrier in space. It is a one-way boundary in space-time. Outside the event horizon, there are still possible paths that lead outward. A rocket might escape if it has enough fuel. A particle might move away. A beam of light can still travel to the wider universe, provided it begins outside the boundary and is aimed along a path that escapes. But inside the horizon, every future directed path leads deeper in. This includes the path of a spacecraft, the path of a falling stone, the path of a radio signal, and the path of light itself. That is why the event horizon is sometimes described as a point of no return. But even that phrase can be slightly misleading, because it can make the horizon sound like a dramatic cliff edge. In the case of a very large black hole, especially a supermassive black hole, crossing the event horizon might feel locally uneventful. Imagine an astronaut falling freely toward a supermassive black hole. If the black hole is large enough, the tidal forces at the event horizon may still be mild. Tidal forces are differences in gravity from one part of the astronaut's body to another, and near the horizon of a giant black hole, those differences can be surprisingly small. The astronaut might pass the horizon without feeling a sudden tug, shock, or tearing force at that exact crossing point. Their watch would keep ticking, their breathing would continue, a small object floating beside them would still drift nearby. Locally, in the immediate region around the astronaut, the laws of physics would seem normal for a while. There would be no helpful sign saying, "You have now entered the black hole, please enjoy your irreversible journey." From far away, however, the story looks completely different. A distant observer watching the astronaut fall would see the astronaut appear to slow down as they approach the event horizon. The astronaut's clock would seem to tick more and more slowly. Their signals would arrive increasingly delayed. Their image would become dimmer and redder. Eventually, they would appear to fade from view. This happens because of gravitational time dilation and gravitational redshift. Gravitational time dilation means that time passes differently in different gravitational environments. A clock deep in a strong gravitational field appears to run slowly compared with a clock far away. This is not an illusion caused by faulty eyesight. It is a real feature of space-time described by general relativity. Gravitational redshift is closely related. As light climbs out of a strong gravitational field, it loses energy. Since light with lower energy has a longer wavelength, the light becomes redder. Near a black hole, this stretching can become extreme. Signals sent from an object near the event horizon are stretched to longer and longer wavelengths as they struggle outward. So, to the distant observer, the astronaut never quite appears to cross the horizon in ordinary external time. Instead, the astronaut seems to slow, redden, and fade, becoming harder and harder to detect. In practice, the final light becomes so faint and so stretched that the astronaut vanishes from observation. But for the astronaut, their own proper time tells another story. Proper time is the time measured by a clock travelling along with the observer. In their own proper time, the astronaut crosses the event horizon in a finite interval. They do not hover forever at the boundary. They do not see their own clock freeze. They simply continue inward. Both viewpoints are part of the same physics. The distant observer describes what can be seen from outside. The falling astronaut describes what happens along their own path. General relativity allows these descriptions to differ, because time is not a universal background ticking identically for everyone everywhere. This distinction was not always easy to understand. Early descriptions of the Schwarzschild black hole made the event horizon look mathematically strange, almost as though something physically disastrous happened there. In the original Schwarzschild coordinates, the equations behaved badly at the Schwarzschild radius. It took later work to clarify that this was a problem with the coordinate system, not a true physical singularity at the horizon. David Finkelstein helped show that the event horizon could be understood as a one-way surface in spacetime. Martin Kruskal, along with George Sikaris, developed coordinates that extended the Schwarzschild solution more smoothly across the horizon. These coordinate descriptions helped reveal that the event horizon itself is not where spacetime curvature becomes infinite. The true classical singularity lies deeper inside. A simple comparison is the horizon at sea. From a beach, the horizon looks like a distant edge where the world might end. But if you sail toward it, you do not strike a wall. The horizon is not a physical object floating on the water. Of course, a black hole's event horizon is much more absolute than the horizon at sea, because it is not merely a limit of vision. It is a limit of what can ever influence the outside universe. The key idea is one-way causal traffic. Outside the event horizon, the future still has options. Inside it, the future narrows. All roads lead inward, not because a new force suddenly appears, but because the possible directions through space-time have been rearranged. That is the quiet strangeness of the event horizon. It may not feel like a boundary when crossed, yet it changes the meaning of escape completely. Once the horizon is behind you, the most important change is not that gravity has suddenly become a different kind of force. The most important change is that the future no longer contains a path back out. Falling into a black hole sounds as though it should feel dramatic from the very first moment. It is natural to imagine a boundary where everything suddenly changes, as if the event horizon were a surface that could be crossed with a shudder, a flash, or some deep cosmic click. But for a freely falling observer, especially near a very large black hole, the crossing itself may feel surprisingly ordinary. This is one of the stranger lessons of general relativity. A black hole can change your ultimate fate completely, without locally announcing that change at the event horizon. There is no solid barrier there, no physical wall, no glowing membrane, nothing for a falling astronaut to strike, pierce, or bounce from. The horizon is a boundary in causality, not a surface made of material. From the astronaut's own point of view, their clock keeps ticking normally. Their heartbeat continues. Their thoughts unfold one after another. A small object floating beside them remains nearby, at least for a while. The local laws of physics do not suddenly switch off as the horizon is crossed. A light beam in a small cabin still travels at the speed of light. A dropped object beside them still seems to float if everything is falling together. This is because, according to general relativity, a freely falling observer does not feel their own free fall. They're moving along a natural path through curved space-time called a geodesic. A geodesic is the straightest possible path through curved space-time. It is the route an object follows when nothing is pushing it away from its natural motion. No rocket engines, no surface holding it up, no force from the floor pressing against its feet. On Earth, we feel weight because the ground prevents us from following our natural falling path toward Earth's center. The floor pushes upward on our feet. A chair pushes upward when we sit. The planet is constantly interrupting our free fall, which is rather considerate of it. In orbit, astronauts feel weightless not because Earth's gravity has disappeared, but because they and their spacecraft are falling together along similar geodesics. The same principle applies near a black hole. If an astronaut falls freely, they may feel weightless. They are not being dragged through space in the ordinary sense. They are following the path that the curved space-time around the black hole gives them. This can feel deeply counterintuitive. From the outside, a black hole seems like the strongest gravitational trap imaginable. Surely crossing the event horizon should feel like something. Surely the universe should give some local warning that the most important boundary has just been passed. But the event horizon is not defined by what a falling observer feels at that exact point. It is defined by whether any future path can carry light, matter, or information back to the outside universe. Locally, for a small region and a short time, physics can remain ordinary. Globally, everything has changed. Before crossing the horizon, there are still future-directed paths that lead away from the black hole. After crossing it, there are none. The falling astronaut may not feel a sudden force appear, but the set of possible futures has been rearranged completely. The experience depends strongly on the size of the black hole. A stellar mass black hole formed from the collapse of a massive star may have a mass of several suns or several tens of suns. Its event horizon might be only tens or hundreds of kilometers across. That is large by human standards, but tiny by astronomical standards. Around such a compact object, space-time curvature changes sharply over short distances. This creates intense tidal forces. Tidal forces are differences in gravity from one part of an object to another. If an astronaut falls feet first toward a small black hole, the pull on their feet can become much stronger than the pull on their head. The result is stretching along the direction of fall and squeezing from the sides. Near a small enough black hole, this effect could become fatal before the astronaut even reaches the event horizon. A supermassive black hole is different. Its mass is vastly greater, but its event horizon is also vastly larger. This is one of the strange scaling features of black holes. The more massive a black hole is, the larger its event horizon becomes. And because that horizon is spread over a much larger region, the tidal gradient at the horizon can actually be weaker. The tidal gradient means how quickly the gravitational effect changes from one place to another. For a small black hole, the change across a human body can be enormous near the horizon. For a supermassive black hole, the change across the same body at the horizon can be mild. The total situation is still inescapable, of course. This is not the universe offering a luxury black hole experience, but the boundary itself can be crossed without immediate destruction. Sagittarius, a star, the supermassive black hole at the centre of the Milky Way, has about 4 million solar masses. Its event horizon is millions of kilometres across. Messier 87 star, the black hole imaged by the Event Horizon Telescope in the galaxy Messier 87, has several billion solar masses. Around black holes like these, the horizon is so large that a falling observer could, in principle, pass through it before tidal forces became overwhelming. Crossing the event horizon does not mean reaching the singularity instantly. In the falling observer's own proper time, there remains a finite inward journey. Proper time is the time measured by a clock travelling with the observer. For that observer, time continues. The event horizon is crossed. The fall continues. The central region lies ahead. For a smaller stellar mass black hole, the remaining time before reaching the singularity may be very short. For a supermassive black hole, the inward journey can be longer. But in the classical picture of a simple black hole, the direction is no longer optional. Every future-directed path leads deeper inward. That is the quiet strangeness of falling through the horizon. The boundary may pass without drama, but its meaning is absolute. Nothing local needs to shout. Nothing solid needs to break. The black hole does not announce itself at the edge because the event horizon is not an edge in the ordinary sense. It is the place where escape has disappeared from the future. And although that crossing may be calm for a while, the calm cannot last forever. Deeper inside, space-time curvature grows stronger. The differences from one part of a falling object to another become larger. The horizon may pass quietly, but tidal forces eventually become impossible to ignore. Tidal forces are what happen when gravity does not pull on every part of an object equally. That may sound like a small detail, but near a black hole, small details can become rather committed to ruining your afternoon. Gravity itself is not the whole problem. If every part of a falling object were pulled in exactly the same way, the object would simply fall. It would feel weightless, at least locally, because all of its parts would be moving together along similar paths through space-time. The danger begins when one part is pulled differently from another. On Earth, tidal forces are familiar in a gentle form. The Moon's gravity pulls a little more strongly on the side of Earth nearest the Moon than on the far side. This difference helps raise ocean tides. The same basic principle also appears in the way planets, moons and rings interact across the solar system. Most of the time, these effects are slow and graceful enough to seem almost peaceful. Near a compact black hole, the same idea becomes extreme. Imagine falling feet first toward a black hole. Your feet are closer to the black hole than your head. Because gravity becomes stronger at smaller distances, your feet are pulled more strongly than your head. This difference creates stretching along the direction of fall. Your body is not merely being pulled inward as a single object, it is being pulled unevenly, with the nearer parts guided more sharply inward than the farther parts. At the same time, the sideways directions are squeezed. This is a little harder to picture because gravity is often imagined as a simple downward pull. But in general relativity, the deeper story is spacetime curvature. Nearby paths through curved spacetime can separate in one direction while converging in another. Along the direction toward the black hole, matter is stretched. Across the sideways directions, matter is compressed. This combination of stretching and squeezing is known, rather memorably, as spaghettification. The name sounds almost playful, which is perhaps the universe's way of making an appalling process slightly easier to discuss. Spaghettification means that an extended object is pulled into a long, thin shape by extreme tidal gradients. The radial direction, pointing toward the black hole, is stretched. The transverse directions across the fall are squeezed. Matter is distorted not because the black hole reaches out with a physical hand, but because different parts of the object are following different natural paths through curved space-time. The technical idea behind this is called geodesic deviation. A geodesic is the natural path an object follows through curved space-time when nothing is pushing it away from free fall. Geodesic deviation describes how nearby geodesics move relative to one another. Near a black hole, those paths can diverge and converge so strongly that ordinary matter cannot hold itself together. The strength of spaghettification depends greatly on the black hole's mass. A stellar mass black hole formed from the collapse of a massive star may have only a few times the mass of the Sun, or perhaps tens of solar masses. Its event horizon is relatively small, perhaps only tens or hundreds of kilometers across. Because the mass is concentrated into such a compact region, the gravitational field changes very sharply over short distances. For a person falling toward a small black hole, the difference in gravity between head and feet could become fatal before the event horizon is even reached. In that case, the event horizon itself is still not a wall, but the surrounding tidal forces are already violent enough to tear matter apart outside it. A supermassive black hole behaves differently at the horizon. Sagittarius. A star at the centre of the Milky Way has about 4 million times the mass of the Sun. Messier 87 star in the galaxy Messier 87 has several billion solar masses. Their event horizons are enormously larger than those of stellar mass black holes. Because the horizon is spread across such a vast scale, the tidal gradient at the horizon can be much weaker. This is one of the strange scaling facts about black holes. The more massive the black hole, the larger the event horizon, and the gentler the tidal difference can be at that boundary. A person crossing the horizon of a supermassive black hole might not be torn apart immediately. They could pass through the point of no return before the worst tidal forces arrived. But this is not safety, it is only postponement. Deeper inside the black hole, the tidal forces grow. Eventually, even inside a giant black hole, the differences in space-time curvature become too large for any ordinary structure to survive. A spacecraft would be stretched and crushed. A planet would be disrupted. A human body, molecules, atoms, and nuclei would be driven into conditions where familiar matter can no longer remain organised in ordinary ways. There is a related classical idea called the Roche limit. The Roche limit is the distance within which a smaller object held together by its own gravity can be torn apart by the tidal forces of a larger body. It helps explain why moons can be disrupted near planets, and why rings may form around worlds such as Saturn. But around black holes, tidal disruption enters a much more extreme relativistic environment. The basic idea of uneven gravity still matters, but the full description involves curved spacetime, event horizons, and the limits of general relativity. Astronomers can see dramatic examples of tidal destruction in events called tidal disruption events. These occur when a star passes too close to a supermassive black hole. The side of the star nearer the black hole is pulled more strongly than the far side. The star is stretched, torn apart, and partly drawn into long streams of gas. Some material may escape, while some falls inward and heats as it forms a bright, turbulent flow around the black hole. These events can produce flares of visible light, ultraviolet light, and X-rays. They are not observations of matter after it has crossed the event horizon, but they are powerful evidence of what black hole gravity can do before material disappears from view. The Zwicky Transient Facility helps discover changing objects and sudden flares across the sky. The Hubble Space Telescope can study light from distant tidal disruption events with high detail. The Chandra X-ray Observatory can detect high-energy radiation from extremely hot gas near black holes. Together, these observatories help reveal the violent outskirts of the most hidden objects in the universe. Spaghettification, then, is not just a colourful nickname. It is a real physical consequence of tidal forces. It shows that the danger near a black hole is not simply that gravity is strong, but that gravity changes sharply from place to place. Matter is stretched along the inward direction, squeezed sideways, heated, separated, and stripped of its ordinary structure. Once matter has been stretched, heated, and pulled apart, the next question becomes even stranger. Inside the event horizon, the issue is no longer only what forces act on matter. It is what direction space and time themselves allow matter to take. Inside a black hole, the most important change is not that gravity becomes a stronger version of ordinary gravity. It is that the future itself changes direction. Outside the event horizon, falling inward is dangerous, but it is not yet inevitable in the deepest sense. A rocket might still fire its engines and escape. A particle might still move away. A beam of light might still travel outward and eventually reach distant space. The closer something gets to the horizon, the more difficult escape becomes. But outside the horizon, there are still possible futures that lead away from the black hole. Inside the event horizon, that is no longer true. Once the horizon has been crossed, moving inward is not merely likely. It is not merely what happens if the engines fail, or if the traveller makes a poor navigational choice, or if someone forgets to read the rather important black hole safety leaflet. Moving inward becomes as unavoidable as moving toward tomorrow. It is built into the structure of space-time. This is one of the strangest ideas in general relativity. We usually think of space as something we can move through in different directions. Left, right, up, down, forward, backward. Time feels different. We can move around in space, but we cannot choose not to move into the future. Tomorrow is not optional. It arrives whether we stroll, sprint, nap, or complain gently about the weather. Inside a simple black hole, the inward direction begins to behave more like time in that sense. The smaller radial distance, the direction deeper toward the centre, becomes part of every possible future path. This is sometimes described by saying that space and time switch roles inside a black hole. That phrase can be helpful, but it needs care. Space and time do not simply swap name tags like two confused guests at a very theoretical dinner party. The real point is more precise. Outside the horizon, the radial direction behaves like a spatial direction. An object can move inward or outward, depending on its path and energy. Inside the horizon, the radial direction toward the centre becomes unavoidable for any future directed motion. The falling object cannot choose to remain at the same radius or move back outward, any more than it can choose to remain forever in yesterday. This is not because a new force appears at the horizon. The local pull of gravity does not suddenly become infinite there. In a large black hole, the crossing can still feel quiet, but the global geometry of spacetime has changed. The event horizon is the boundary where outward futures disappear. A helpful way to picture this is through light cones. A light cone is a diagram that shows the possible future path through spacetime from a particular event. At any moment, light can spread outward in all directions at the speed of light. Slower objects such as rockets, planets, stones, and people must travel inside the range of those light paths. In this sense, the light cone marks the boundary of what can be reached or influenced from a particular point. The idea grows out of space-time diagrams, which were developed after Hermann Minkowski showed that Einstein's special relativity could be understood geometrically. Minkowski united space and time into a single mathematical structure, making it possible to draw diagrams where time is one direction, space is another, and light traces out the edges of the possible future. These diagrams became a foundation for thinking clearly about causality. Far from a black hole, light cones stand in a fairly ordinary way. Future paths can point in many spatial directions. A rocket can accelerate left or right. A beam of light can move outward. A signal can be sent away and eventually received elsewhere. Near a black hole, the light cones begin to tilt. This is not because light itself becomes tired, or because the black hole has somehow slowed it down locally. Light still travels at the cosmic speed limit in its own local region. But space-time is curved so strongly that the possible future directions lean inward. At the event horizon, the outward edge of the light cone is balanced at the boundary. This is the last place where an outward moving light ray can, in a sense, remain on the edge. Inside the horizon, the entire future light cone points towards smaller radial distance. Even the path of light aimed outward still leads inward. It can move locally at the speed of light, but the geometry of space-time carries that future deeper into the black hole. This is why escape is impossible. It is not just that a rocket would need more fuel. It is not even just that light is not fast enough in the ordinary sense. It is that inside the event horizon, increasing distance from the black hole is no longer within the future light cone. There is no future-directed path that leads back out. A gentle analogy is the river model of a black hole. In this picture, space itself is imagined as flowing inward toward the black hole, like a river moving toward a waterfall. Far from the black hole, the river flows slowly, and a swimmer can still make progress upstream. Closer in, the flow grows faster. At the event horizon, the inward flow reaches the speed of light. Beyond the horizon, the flow is faster than light, so even light trying to swim outward is carried inward. This model has been described in accessible ways by scientists such as Andrew Hamilton and Jason Liesel. It can be useful because it gives the mind something familiar to hold, but it must not be taken too literally. Space is not a physical fluid, and a black hole is not literally a waterfall in a cosmic river. The river model is an analogy for the way space-time geometry shapes possible paths. Still, it captures one essential truth. Inside the horizon, the problem is not a lack of effort. The problem is the direction of the future. A rocket could fire its engines, A flashlight could shine outward. A radio transmitter could send a final message. Locally, each thing behaves according to ordinary physics, but globally, every future-directed path remains trapped. The rocket's future goes inward. The light's future goes inward. The radio signal's future goes inward. Everything that happens inside the horizon remains unable to influence the outside universe. This gives the interior of a black hole its eerie simplicity. There may be many complicated physical processes happening to matter as it falls, especially in a rotating or realistic black hole. Matter may be stretched, heated, squeezed, and torn apart. But in the simplest classical picture, the causal direction is clear. The future points inward, and if the future points inward, then the singularity is not like an ordinary place sitting somewhere in space that one might avoid by steering carefully. In a simple black hole, it is more like a moment in the falling object's future. It is not waiting to the left or right. It is not a destination chosen from a map. It is the place where every possible inward future, according to classical general relativity, is forced to end. The singularity is where the simple picture of falling inward becomes much harder to follow. In classical general relativity, a singularity is a region where space-time curvature becomes infinite. It is the point, or more carefully the boundary of the theory, where the mathematics says that density, gravity and curvature have been pushed beyond all finite limits. The paths followed by falling matter come to an end. The equations stop giving physically meaningful answers. The map does not merely become difficult to read, it runs out of paper. This is why the singularity should not be imagined too literally as a tiny hard object sitting at the centre of the black hole. It is not a little bead of matter. It is not a dense pebble. It is not a miniature planet made of crushed stars tucked away in the middle like the universe's least accessible marble. That image is understandable, but it is misleading. A singularity is better understood as a breakdown in the mathematical description of space-time. General relativity predicts that inside a simple black hole, all future-directed paths lead toward a place where curvature grows without limit. But when a theory predicts an infinity, physicists usually become cautious. Infinity is not always nature calmly giving us a number. Sometimes it is nature, or rather our theory of nature, saying that the rules being used are no longer sufficient. This is an important distinction. General relativity is one of the most successful scientific theories ever created. It explains the orbit of Mercury more accurately than Newtonian gravity. It predicts gravitational time dilation. It predicts the bending of light around massive objects. It predicts gravitational waves, which the Laser Interferometer Gravitational Wave Observatory has directly detected from merging black holes. But even a magnificent theory can have limits. The singularity is one of those limits. For a long time, it was reasonable to wonder whether singularities were just artifacts of overly simple assumptions. Carl Schwarzschild's black hole solution describes a perfectly spherical, non-rotating, uncharged mass. Real collapsing stars are messy. They rotate. They have magnetic fields. They are not perfectly symmetrical. Perhaps, some physicists hoped, singularities appeared only because the mathematics had been made too neat. Like a model house with no dust, no cracks, and absolutely no one leaving socks on the floor. Roger Penrose changed that picture in the 1960s. Penrose's singularity theorem showed that singularities were not just the result of perfect spherical symmetry. Under broad and physically reasonable conditions, gravitational collapse and general relativity leads to incomplete paths through space-time. In other words, the appearance of singularities was not a fragile feature of one idealized solution. It was deeply built into the structure of the theory. This was a profound result. It suggested that when enough mass collapses under its own gravity, general relativity does not merely predict a very dense object. It predicts that space-time itself reaches a boundary. The theory leads to a place where ordinary continuation becomes impossible. Stephen Hawking then extended these ideas into cosmology. Working with Penrose and building on related methods, Hawking showed that singularity theorems could also be applied to the expanding universe. If general relativity is followed backward in time under certain conditions, the universe appears to emerge from a singular state. This connected the mathematics of black hole singularities with the mathematics of the Big Bang. That connection does not mean the Big Bang was simply a black hole in reverse, or that the universe was born from the centre of a black hole in any straightforward way. The situations are different, but it does show something remarkable. The same theory that describes the collapse of matter into black holes also points toward a boundary at the beginning of cosmic history. At both extremes, general relativity seems to tell us that space-time has reached the edge of its own description. This is where the word infinite must be handled gently. In everyday language, infinite can sound like a real thing that exists somewhere, perhaps in a small box that is being very dramatic. In physics, an infinite prediction often means that the theory has left the territory where it can be trusted. When the density of a fluid becomes infinite in an equation, or the curvature of space-time becomes infinite in a model, it may be a sign that some missing physics needs to be included. Near a black hole singularity, the missing physics is almost certainly quantum mechanics. General relativity describes gravity as the curvature of space-time. Quantum mechanics describes matter, energy, particles, fields, and probabilities at very small scales. Each theory works extraordinarily well in its own domain, but general relativity does not include quantum mechanics in a complete way, and quantum theory does not yet include gravity in a fully confirmed form. Near the predicted singularity, both extreme gravity and tiny scales matter at once. That is precisely where our current theories do not fully join. Physicists often use the Planck length and Planck time as markers of where quantum gravitational effects are expected to become important. The Planck length is about 1.6 times 10 to the minus 35 meters, unimaginably smaller than an atomic nucleus. The Planck time is about 5.4 times 10 to the minus 44 seconds. The timelight would take to travel one Planck length. These are not proven pixels of reality, but they are scales where the known constants of gravity, quantum mechanics, and the speed of light meet. At such scales, spacetime may not behave like the smooth curve geometry described by Einstein. It may fluctuate. It may have a discrete structure. It may be replaced by something deeper that only looks like space-time when viewed on larger scales. The honest answer is that we do not yet know. Several candidate approaches try to address this. String theory, associated with many researchers including Edward Witten, suggests that the fundamental ingredients of reality may be tiny extended strings rather than point particles, and it has produced important ideas about black hole entropy and holography. Loop quantum gravity, developed by researchers such as Abhay Ashtekar, Lee Smolin, and Carlo Rovelli, explores whether spacetime geometry itself may be quantized. Asymptotic safety, an approach connected historically with Steven Weinberg, investigates whether gravity may remain mathematically well-behaved at extremely high energies through a special kind of quantum consistency. These approaches are serious scientific attempts to understand quantum gravity, but none has yet been confirmed experimentally as the final theory of what happens inside a black hole. The singularity remains a signpost pointing beyond established physics. So the singularity problem is not merely that black holes are extreme, it is that they expose a gap between our two greatest descriptions of nature. General relativity tells matter how to fall inward. Quantum mechanics tells matter how to behave at small scales. But at the predicted singularity, both are needed, and the completed bridge between them is still missing. And the problem becomes even more subtle when black holes are made more realistic. The simplest black hole does not spin. Real black holes almost certainly do. When rotation enters the picture, the interior changes shape. New regions appear in the mathematics, and the question of what lies inside becomes stranger again. Real black holes almost certainly spin. That may sound like an added detail, as though the universe looked at black holes and decided they were not already dramatic enough. But rotation is not a decorative feature. It is likely one of the most important properties of real black holes, because the stars, gas clouds, and compact objects that form them are almost never perfectly still. In physics, rotation is connected to angular momentum. Angular momentum is the quantity that describes how much turning motion something has. A spinning star has angular momentum. A cloud of gas swirling as it collapses has angular momentum. Two dense objects orbiting one another before they merge have angular momentum. And angular momentum tends to be conserved, meaning it does not simply disappear because the system becomes more compact. A familiar example is an ice skater pulling in their arms and spinning faster. The skater has not created rotation from nowhere. They have changed how their mass is distributed, and the spin speeds up as the body becomes more compact. A collapsing star behaves in a broadly similar way, although with rather more gravity and rather fewer sequins. As its core shrinks, any original rotation can become much faster. So when a massive star collapses into a black hole, or when matter spirals inward over millions of years, or when two black holes merge, rotation is expected. A perfectly non-rotating black hole is useful for learning, but nature rarely takes the simplest classroom example and leaves it untouched. The simplest mathematical black hole is the Schwarzschild black hole. It has mass but no rotation and no electric charge. Carl Schwarzschild's solution was the first exact black hole-related solution to Einstein's field equations, found in 1916. It is beautifully important because it reveals the event horizon and the inward-pointing future of a simple black hole in the cleanest possible way. But real astrophysical black holes are better described by a different solution, the Kerr black hole. The Kerr black hole was discovered mathematically by Roy Kerr in 1963. It describes an uncharged rotating black hole in general relativity. This is a major step closer to reality, because black holes in the universe are expected to spin. The Kerr solution is not just the Schwarzschild solution with a casual twirl added. Rotation changes the structure of spacetime around the black hole in deep ways. One of those changes is frame dragging. Frame dragging is the twisting of spacetime around a rotating mass. In general relativity, mass and energy curve spacetime, but a rotating mass can also drag spacetime around with it. The effect exists around any rotating object, including Earth, but around Earth it is extremely weak. Gravity Probe B, a satellite mission launched by the National Aeronautics and Space Administration, measured this tiny frame dragging effect by tracking the orientation of very precise gyroscopes in orbit around Earth. Around a rotating black hole, frame dragging becomes far stronger. Spacetime itself is twisted around the black hole's rotation. It is not simply that matter is being pulled inward. The very geometry through which matter moves is being stirred. This creates a remarkable region called the ergosphere. The ergosphere lies outside the event horizon of a rotating black hole. Inside the ergosphere, space-time is dragged around so strongly that nothing can remain still relative to distant stars. Even light must participate in the rotation in some way. An object can still escape from the ergosphere if it has the right motion, because the ergosphere is outside the event horizon. but it cannot simply hover motionless against the rotation of space-time. The ergosphere is one of the clearest signs that rotation makes black holes richer and stranger than the non-rotating picture. It also opens a theoretical possibility known as the Penrose process. Roger Penrose proposed that energy could, in principle, be extracted from a rotating black hole. In the Penrose process, an object enters the ergosphere and splits into two pieces. One piece falls into the black hole with a kind of negative energy relative to the distant universe, while the other escapes with more energy than the original object had when it entered. The extra energy comes from the black hole's rotation. In effect, the black hole is slowed down slightly. This is not a practical engineering scheme for anyone hoping to reduce their electricity bill, but it is physically important because it shows that a rotating black hole stores usable rotational energy. Related ideas also help explain how magnetic fields near spinning black holes may power enormous astrophysical jets. The Kerr black hole also changes the predicted interior. In the ideal mathematical solution, the singularity is not a point, it is a ring singularity. Instead of all matter being forced toward a central point-like end, the mathematics describes a ring-shaped region where the classical theory breaks down. The ideal Kerr solution also contains an inner horizon, sometimes called a Cauchy horizon. This is a boundary deeper inside the black hole where the predictability of the space-time becomes deeply problematic. Beyond such a horizon in the exact mathematical solution, the structure can appear to open into strange possible extensions, sometimes discussed in connection with other regions of space-time. But this is where caution becomes essential. The exact Kerr solution is highly idealized. It describes a perfectly clean, rotating black hole, not one disturbed by radiation, infalling matter, quantum effects, gravitational waves, or the general messiness of the real universe. Real black holes are not kept in pristine mathematical packaging. Many physicists expect the inner horizon of a rotating black hole to be unstable. Even tiny disturbances may become enormously amplified there. This leads to an effect called mass inflation, studied by Eric Poisson and Werner Israel. Mass inflation is a theoretical instability near the inner horizon, where the energy associated with crossing radiation streams can grow without limit in the classical description. In simple terms, the inner horizon may not be a calm gateway to exotic regions at all. It may be transformed by instability into a violent zone where the ideal Kerr picture breaks down. So rotation makes black holes more realistic, but also more complicated. The Schwarzschild black hole gives the cleanest first picture, an event horizon, inward-pointing futures, and a central singularity. The Kerr black hole adds spin, frame dragging, an ergosphere, possible energy extraction, an inner horizon, and a ring singularity. It is closer to nature, but also far less simple. This matters because asking what happens inside a black hole depends on which black hole we mean. A non-rotating black hole gives one idealized answer. A rotating black hole gives a richer and more uncertain one. And real black holes, fed by gas, shaped by magnetic fields, and disturbed by their surroundings, may be stranger still. Before imagining whether anything could pass through the exotic inner structures predicted by the ideal Kerr solution, it helps to return to the outside and ask what black holes actually do to matter as it falls in. Because long before matter reaches any inner horizon or ring singularity, it is often heated, torn, accelerated, and forced into one of the most energetic environments in the universe. Most matter does not fall into a black hole in a neat, silent line, like crumbs politely disappearing into a drain. In the real universe, matter usually arrives with motion, heat, charge, turbulence, and angular momentum. It does not simply drop straight inward. it swirls. Around many black holes, falling material gathers into an accretion disk. An accretion disk is a flattened, rotating flow of gas, dust, plasma, and disrupted stellar material. It forms because matter approaching a black hole usually has some sideways motion. Instead of plunging directly into the event horizon, it begins to orbit, spiral, collide, heat up, and gradually lose energy before moving inward. This disk can become one of the brightest structures in the universe. That may sound strange because black holes are famous for not letting light escape. But the glow around a black hole usually does not come from inside the event horizon. It comes from material outside it. The black hole itself remains dark in the strict sense. The surrounding matter is the part that shines. As gas spirals inward, different parts of the disk orbit at different speeds. Inner regions move faster than outer regions. This creates friction-like effects, turbulence, and powerful stresses within the plasma. Magnetic fields also thread through the disk, helping move angular momentum outward so that some material can fall farther inward. At the same time, gravitational energy is converted into heat and radiation. The result can be astonishing. Accretion disks around black holes can reach temperatures of millions of degrees. At those temperatures, matter is not made of ordinary cool atoms drifting gently along. It is ionized plasma, a hot mixture of charged particles, electrons, atomic nuclei, and intense electromagnetic fields. The disk can shine in visible light, ultraviolet light, and especially X-rays. X-rays are a sign of extremely energetic environments. They are far more energetic than ordinary visible light, and they are often produced by very hot gas near compact objects such as neutron stars and black holes. When astronomers detect powerful X-ray emission from a region where matter is orbiting something massive and compact, it can be an important clue that a black hole may be present. One of the most famous examples is Cygnus X1. Cygnus X1 was one of the first strong stellar mass black hole candidates. It is an X-ray source in a binary system, where a massive visible star orbits an unseen compact companion. The system attracted enormous attention because the unseen object seemed too massive to be a neutron star, making a black hole the best explanation. Astronomers Thomas Bolton, Louise Webster, and Paul Murdin were among those involved in the early identification of Cygnus X1 as a powerful black hole candidate. Their work helped move black holes from mathematical prediction into observational astronomy. The idea was no longer just that equations allowed black holes. The sky itself seemed to be offering examples. In systems like this, matter can be pulled from a companion star and drawn into a disk around the compact object. As the gas spirals inward, it heats and radiates. Some of it may eventually cross the event horizon, but before that final crossing, it can announce its presence loudly across the electromagnetic spectrum, which is quite an achievement for material falling into something famous for silence. Around supermassive black holes, accretion can be even more spectacular. In active galactic nuclei and quasars, enormous amounts of gas fall towards central black holes, with millions or billions of times the mass of the Sun. The accretion disks around these black holes can outshine entire galaxies, not because the black hole interior is glowing, but because the surrounding matter is converting gravitational energy into radiation with incredible efficiency. Some spinning black holes also produce relativistic jets. These are narrow streams of particles launched from regions near the black hole, often along the rotation axis. The particles in these jets can travel at speeds close to the speed of light and can extend across thousands or even millions of light years. They are among the largest and most energetic structures known in the universe. The exact details of jet formation are complex, But magnetic fields and black hole rotation appear to be central. Near a spinning black hole, magnetic fields can become twisted and amplified by the rotating plasma and by frame dragging. These fields can help channel particles away from the central region in tightly focused beams. Roger Blandford and Roman Zanayak described an important mechanism for extracting energy from a rotating black hole through magnetic fields. In the Blandford-Zanayak mechanism, magnetic field lines threading the region near a spinning black hole can tap into the black hole's rotational energy. This process may help power the jets seen in many active galaxies. In simple terms, a spinning black hole can act as part of an enormous cosmic engine, though admittedly not one that fits neatly into the garage. The journey of matter toward a black hole is therefore not usually quiet. It may involve shock waves, magnetic turbulence, nuclear particles, radiation, high-energy photons, and plasma heated to unimaginable temperatures. Matter can be stretched by tides, shredded into streams, flattened into a disk, and accelerated until it becomes part of one of the most violent environments in astrophysics. But once matter crosses the event horizon, its detailed story becomes hidden from the outside universe. From the external point of view, the black hole can still change. If matter falls in, the black hole's mass increases. If the matter carries angular momentum, it can affect the black hole's spin. If it carries electric charge, it can in principle affect the black hole's charge, though real astrophysical black holes are expected to remain nearly neutral overall. Energy, mass, electric charge, and angular momentum all contribute to the black hole's external properties. What disappears from outside view is the detailed internal arrangement. The atoms, molecules, radiation patterns, shapes, textures, histories, and structures of the infalling matter can no longer be directly observed. A star, a gas cloud, a planet, or a dropped notebook may differ enormously before crossing the horizon, but after crossing, the outside universe can describe the resulting black hole only through a few broad properties. This is one of the reasons black holes became so important to theoretical physics. They seem to take complicated matter and hide its details behind an event horizon. Yet physics normally keeps careful accounts. Energy is conserved, charge is conserved, angular momentum is conserved. Quantum mechanics also suggests that information should not simply vanish from reality. So matter falling in creates a deeper puzzle. It is not only a question of where the material goes, it is a question of what happens to its physical information once the outside universe can no longer see it. And that question led to a surprising bridge between black holes and thermodynamics. If matter disappears from view, and if black holes can grow when they absorb energy, then perhaps black holes are not just gravitational objects. Perhaps they also have entropy. Perhaps, in a strange and careful sense, they even have temperature. Entropy sounds at first like a strange thing to connect with black holes. Usually, entropy belongs to warmer and more familiar situations. It appears when steam spreads through a room, when ice melts into water, when heat flows from something hot to something cold, or when a neatly organized desk slowly becomes an archaeological record of snacks, notes, and cables. Entropy is often loosely described as disorder, but the deeper meaning is more precise. Entropy measures how many microscopic arrangements could produce the same large-scale appearance. A cup of hot tea, for example, looks simple from the outside. It has a temperature, a volume, and a certain amount of liquid. But inside it, there are enormous numbers of molecules moving in countless possible ways. Many different microscopic arrangements of those molecules would still look like the same cup of tea at the large scale. The more possible microscopic arrangements there are, the greater the entropy. For ordinary objects, entropy is connected to the hidden details beneath the surface. A cloud of gas may look smooth from far away, but its molecules can be arranged and moving in an extraordinary number of ways. A star may look like a glowing sphere. but inside it there are layers of plasma, radiation, magnetic fields, nuclear reactions and particles following countless paths. Black holes seemed at first to be the opposite. From the outside, a black hole appears remarkably simple. According to classical general relativity, a settled black hole can be described by only a few properties: its mass, its electric charge, and its angular momentum, meaning its spin. That is a shockingly short description for something that may have formed from a collapsing star, swallowed gas clouds, absorbed planets, merged with other black holes, and consumed matter with all kinds of complicated histories. This is the idea behind the phrase, "black holes have no hair," associated with John Archibald Wheeler. It does not mean black holes are especially committed to a smooth appearance, although in a mathematical sense they rather are. It means that black holes hide almost all the detailed information about the matter that formed them. From the outside, the fine details seem shaved away. A black hole made from a star and a black hole made from the same total mass of gas, radiation, and unfortunate furniture would look the same if their mass, charge, and spin were the same. This raised a deep thermodynamic puzzle. If matter with entropy falls into a black hole, where does that entropy go? Suppose a hot cloud of gas falls across the event horizon. Before falling in, that gas has entropy because its particles can be arranged in many microscopic ways. After crossing the horizon, the outside universe can no longer access those details. If the entropy simply vanished from the outside world, the second law of thermodynamics would be in trouble. The second law says that the total entropy of an isolated system should not decrease. Jacob Bekenstein proposed a bold answer in the early 1970s. He argued that black holes themselves must have entropy. More specifically, black hole entropy should be proportional to the area of the event horizon, not the volume inside it. That was astonishing. For ordinary objects, it feels natural to expect entropy to scale with volume. A bigger box of gas can contain more particles and more possible microscopic arrangements. But a black hole seemed to follow a different rule. Its entropy was linked to the area of its horizon, the two-dimensional boundary surrounding the hidden interior. This suggested that the event horizon was not just a point of no return. It was somehow connected to the hidden, microscopic bookkeeping of the black hole. At first, the idea was controversial. If black holes have entropy, then by the usual laws of thermodynamics, they should also have a temperature. And if they have a temperature, they should radiate. But classical general relativity says that nothing escapes from inside a black hole. A black hole that radiates sounds almost like a locked box that quietly posts letters. Then Stephen Hawking made the puzzle even stranger. In 1974, Hawking studied what happens when quantum fields are considered in the curved spacetime around a black hole. Quantum field theory says that what we call empty space is not simply blank nothingness. Fields exist everywhere, and their quantum behavior can be affected by gravity and horizons. Hawking found that black holes should emit thermal radiation. This radiation is now called Hawking radiation. It is radiation predicted when quantum fields are treated in the curved space-time near a black hole's event horizon. It does not mean ordinary light is escaping from inside the horizon. Rather, it arises from the quantum behavior of fields in the black hole's surrounding geometry, as seen by distant observers. The result gave black holes a temperature. It also confirmed in a deeper way that Bekenstein's entropy was not just a metaphor. Black holes really seem to obey laws resembling the laws of thermodynamics. There is, however, a curious twist. Larger black holes are colder. A black hole with the mass of the Sun would have an extremely tiny Hawking temperature, far below the temperature of the cosmic microwave background, the faint afterglow of the early universe. Stellar mass black holes and supermassive black holes today are colder than the radiation bathing the universe around them. They absorb far more energy from their environment than they lose through Hawking radiation. Tiny black holes, if they existed, would be hotter and could radiate more strongly. But ordinary astrophysical black holes radiate so weakly that Hawking radiation has never been directly observed from them. The prediction is theoretically powerful, but observationally almost impossibly faint for large black holes. Still, the meaning is enormous. Black hole entropy links three great areas of physics that usually live in separate rooms: gravity, quantum theory, and thermodynamics. Gravity gives the event horizon. Quantum theory gives Hawking radiation. Thermodynamics gives entropy and temperature. Around black holes, these ideas are forced to speak to one another. No ordinary star or planet does this in quite the same way. A star has heat and entropy, but it does not hide its interior behind a causal boundary. A planet has structure and temperature, but it does not make spacetime into a one-way trap. A black hole combines simplicity on the outside with enormous hidden depth, and then adds quantum radiation just to make sure nobody gets too comfortable. This changes the question of what happens inside a black hole. If black holes have entropy, then the hidden interior may be connected to microscopic states we do not yet understand. If black holes radiate, then over unimaginable spans of time they can lose energy and perhaps eventually evaporate. And if they can evaporate, then the fate of everything that fell inside becomes more than a gravitational mystery. It becomes an information problem, because if matter disappears behind the horizon and the black hole later radiates away, then physics must ask a very careful question. What happened to the information that went in? The black hole information paradox begins with a simple but deeply uncomfortable question. Can the universe forget? In ordinary life, forgetting is easy. A person can forget a password, a name, or why they walked into a room, which remains one of the great unsolved mysteries of domestic physics. But in fundamental physics, information has a stricter meaning. It is not just a message, a memory, or something written in a notebook. Information means the complete physical detail needed to describe a system state. In quantum mechanics, this means the full quantum state of a system. It includes everything needed in principle to describe the particles, fields, correlations, energies, positions, momenta, spins, and probabilities that make the system what it is. A book, a star, a cloud of gas, and a cup of tea are different, not just because they look different to us, but because their microscopic physical states are different. Quantum mechanics is built around the idea that this information is preserved in a closed system. This is called unitary evolution. Unitary evolution means that if you knew the complete quantum state of a system at one time, the laws of quantum mechanics would, in principle, allow the complete state to be traced forward or backward. The information can become scrambled. It can become fantastically difficult to recover. It can be mixed into heat, radiation, and correlations so subtle that no practical creature could reconstruct it. But it is not supposed to be fundamentally destroyed. Black holes seem to challenge that. According to general relativity, matter can fall across an event horizon and disappear from the outside universe. Once it has crossed, no signal can return. A star, a planet, a gas cloud, a book, or one very unlucky sandwich can all enter the black hole, and from the outside the black hole eventually settles down to a very simple description: mass, electric charge, and angular momentum. The fine details appear hidden. At first, that might sound acceptable. Perhaps the information is simply inside the black hole. It has not been destroyed, only placed somewhere no outside observer can reach. That is strange, but not necessarily fatal to physics. The difficulty becomes sharper because of Hawking radiation. Stephen Hawking's calculations showed that black holes should emit thermal radiation due to quantum field effects in the curved spacetime near the event horizon. This means that over immense timescales, a black hole can lose energy and slowly evaporate. If the black hole eventually disappears completely, then the question becomes unavoidable. What happened to the information about everything that fell in? This is the black hole information paradox. General relativity seems to allow information to disappear behind the event horizon and perhaps vanish with the black hole. Quantum mechanics says that information in a closed system should not be destroyed. Both theories are extraordinarily successful in their own domains, yet here they appear to disagree. The original problem with Hawking radiation was that it seemed thermal and featureless. Thermal radiation is radiation described mainly by temperature. It looks random in the relevant sense. It does not obviously carry the detailed information about whether the black hole formed from a collapsing star, swallowed a cloud of hydrogen, or absorbed a library with extremely poor timing. If the radiation is perfectly thermal, then it cannot carry out the fine details of what fell in. That would mean a pure quantum state could evolve into a mixed thermal state, which violates ordinary unitary evolution. In calmer words, the universe would have lost part of its own account book. Physicists tend to become nervous when the account book catches fire. Don Page helped sharpen the discussion with what is now called the Page curve. The Page curve describes how the entanglement entropy of Hawking radiation should change if black hole evaporation preserves information. At first, the radiation appears increasingly entangled with what remains inside the black hole. But after a certain point, often called the Page time, information should begin to emerge in subtle correlations within the radiation. If quantum mechanics remains unitary, the curve should eventually come back down, showing that the complete radiation is not merely featureless heat. This does not mean information comes out in an easy-to-read form. It would not be like the black hole neatly printing a receipt. The information would be scrambled across extremely delicate quantum correlations in the radiation. But in principle, it would not be destroyed. Several major ideas grew from this tension. Gerard de Hooft and Leonard Susskind developed the holographic principle, which suggests that the information inside a region of space may be encoded on its boundary. This idea was partly inspired by black hole entropy, which depends on the area of the event horizon rather than the volume inside. That is a startling clue that the boundary of a region may carry deeper information than ordinary intuition would expect. Juan Maldacena then introduced the anti-de Sitter and conformal field theory correspondence. This is a precise theoretical relationship between a gravitational theory, in a kind of space-time called anti-de Sitter space, and a quantum field theory, without gravity on its boundary. It does not describe our universe in a direct, simple way, because our universe is not known to be anti-de Sitter space. But it provides a major clue that some gravitational systems can preserve information completely. Modern theory now strongly leans toward information not being fundamentally destroyed. Many physicists suspect that Hawking radiation is not perfectly featureless after all, and that the information escapes in subtle quantum correlations. But the full answer for real, astrophysical black holes in our universe is still not completely settled. The paradox remains one of the places where gravity, quantum mechanics, space-time, and thermodynamics press most tightly together, and as scientists tried to solve it, the inside of a black hole became stranger rather than simpler. The event horizon might be smooth, or it might hide new quantum structure. The interior might resemble the classical picture, or it might be replaced by something more radical. Attempts to save information have opened the door to firewalls, fuzzballs, complementarity, and other possibilities that ask whether a black hole's interior is truly the empty falling region that general relativity first seemed to promise. The classical picture of a black hole is, in a strange way, almost peaceful at the horizon. For a large black hole, general relativity says that a freely falling observer should be able to cross the event horizon without anything locally dramatic happening at that exact boundary. There is no solid surface. There is no flash of infinite heat. There is no sudden wall where spacetime announces, with unnecessary theatrical confidence, that the traveller has entered the mysterious zone. Instead, the falling observer simply continues along a natural path through curved spacetime. Their own clock keeps ticking. Their local surroundings remain normal for a while. If the black hole is supermassive, the tidal forces at the horizon may be gentle enough that the crossing feels uneventful. The outside universe has become unreachable, but the horizon itself may not feel like a place at all. This calm crossing is one of the most beautiful consequences of Einstein's equivalence principle. A small, freely falling observer should not feel gravity as a force in their immediate surroundings. Locally, free fall can feel weightless, and if the event horizon is not a physical surface, then crossing it should not necessarily involve a local shock. But quantum information has made this peaceful picture much harder to keep. The information paradox asks whether the information about everything that falls into a black hole is preserved or destroyed. Quantum mechanics strongly suggests that information should be preserved in a closed system. Hawking radiation, however, originally seemed thermal and featureless, as though it could not carry out the detailed information about what fell in. If the black hole eventually evaporates, then the information appears to have nowhere obvious to go. Attempts to solve that problem have led to some very strange possibilities, and one of the most dramatic is the firewall proposal. The firewall proposal was introduced by Ahmed Al-Amheri, Donald Maroff, Joseph Polchinski, and James Sully. It is sometimes known by the initials of their surnames, though for voiceover it is better simply to call it the firewall argument. The proposal suggests that an observer falling into an old black hole might not cross a smooth horizon at all. Instead, they might encounter high-energy quanta at or near the event horizon. In simpler terms, the horizon could become violently hot. This is not a small adjustment to the classical picture. It is a serious challenge to one of the gentlest assumptions about large black holes. In general relativity, the horizon of a large black hole should be locally uneventful for a falling observer. In the firewall proposal, the horizon becomes a destructive boundary. The traveller does not pass through quietly. They meet something energetic enough to ruin both the journey and, presumably, the mood. Firewalls are controversial because they threaten Einstein's equivalence principle. If the horizon becomes a violent place, then free fall across the horizon is no longer locally ordinary. The event horizon stops being a smooth causal boundary and becomes something with physical drama. That would mean quantum mechanics, black hole thermodynamics, and general relativity cannot all remain in their simplest forms at the same time. The firewall argument comes from a conflict involving quantum entanglement. Hawking radiation emitted late in a black hole's life seems to need to be entangled with earlier Hawking radiation if information is to escape. But ordinary quantum field theory near a smooth horizon also requires certain entanglements across the horizon. Quantum mechanics limits how entanglement can be shared. A quantum system cannot be fully entangled with two independent systems at once in the required way. This tension leads to the possibility that the smooth horizon must break down. That is the rough heart of the firewall idea. It is not that someone simply imagined a wall of fire because black holes needed more personality. It is an attempt to take quantum information seriously. Another possibility comes from string theory and is known as the fuzzball proposal. The fuzzball proposal is associated especially with Samir Mathur and collaborators. In this view, black holes may not have empty interiors in the classical sense. Instead, what we call a black hole could be a horizon-sized quantum object made of complicated string theory states. The event horizon and interior of the traditional black hole may be replaced by a vast, tangled quantum structure. The name fuzzball sounds almost soft, which is slightly unfair to how difficult the mathematics can be. The idea is not that black holes are literally fluffy cosmic pom-poms. Rather, the word points to the possibility that the black hole is not smooth and empty at the horizon. Its microscopic quantum structure may extend all the way out to where the horizon would have been in the classical picture. This could help with the information problem because the information would not need to disappear into a featureless interior. It could be stored in the enormous number of quantum states making up the fuzzball. Hawking-like radiation might then carry information away from this structure, instead of emerging as perfectly featureless thermal radiation from an empty horizon. In the fuzzball picture, the black hole interior is radically changed. The classical idea of falling through an empty horizon into a hidden region may be only an approximation, useful for certain large-scale descriptions but not the final microscopic truth. Then there is black hole complementarity. Black hole complementarity is associated with Leonard Susskind, Larus Thorlacius, and Gerard 't Hooft. It tries to preserve both the outside and falling descriptions without allowing any single observer to witness a contradiction. From the outside observer's point of view, information may be absorbed, scrambled, and eventually returned in Hawking radiation near the horizon. From the falling observer's point of view, nothing special happens at the horizon, and they continue inward. These two descriptions seem incompatible if treated as one single story from one viewpoint. But complementarity suggests that they are both valid descriptions for different observers, and no observer can compare them directly. The falling observer cannot send a report back after crossing the horizon. The outside observer never receives information from inside in the ordinary way. The event horizon prevents the contradiction from being physically checked by a single witness. This is a subtle idea. It does not say anything goes. It does not say physics can simply keep two stories because they are both charming in different lighting. It says that the rules of observation and causality around black holes may prevent the conflicting descriptions from ever being combined into one operational contradiction. All of these proposals are serious scientific attempts to preserve quantum mechanics while respecting what black holes have taught us. Firewalls, fuzzballs, and complementarity are not science fiction exits from black holes. They are not convenient loopholes for escaping the point of no return. They are attempts to understand whether the interior described by classical general relativity survives once quantum information is included. And this distinction matters. A firewall is not a portal, a fuzzball is not a tunnel. Complementarity is not a secret rescue plan. These ideas are not there to make black holes safer or more convenient. If anything, they make black holes even more conceptually demanding. They also remain unconfirmed. No firewall has been observed. No fuzzball has been experimentally verified as the true description of an astrophysical black hole. Black hole complementarity remains a theoretical idea rather than a directly tested fact. The black holes observed by the Event Horizon Telescope and by gravitational wave detectors behave so far in ways broadly consistent with general relativity outside the horizon. But those observations do not yet reveal the microscopic truth of the interior, so the honest picture is layered again. Classical general relativity gives a smooth horizon for a large black hole. Quantum information arguments suggest that this smooth picture may be incomplete. Firewalls suggest the horizon could be violent. Fuzzballs suggest the interior might be replaced by quantum structure. Complementarity suggests different observers may have different but non-contradictory descriptions. Each possibility is trying to answer the same underlying question. How can black holes hide information, radiate, obey thermodynamics, and still respect quantum mechanics? And once physicists began asking whether the classical interior must be replaced or reinterpreted, another old and tempting question returned. If black holes distort space-time so profoundly, could they connect to somewhere else? Could the mathematics that creates a black hole also create a bridge, a passage, or another region beyond the one we know? Wormholes are one of those ideas that seem to appear whenever black holes become too mysterious to resist. If a black hole is a place where space-time bends so deeply that nothing can escape, then it is natural to wonder whether the bending might continue somewhere else. Perhaps the black hole is not only an ending, perhaps it is a passage. Perhaps it connects to another region of space, another time, or even another universe. It is a tempting thought, partly because it turns the black hole from a final destination into a doorway. But nature is not obliged to make the tempting answer the correct one. The scientific idea begins with something called an Einstein-Rosen bridge. In 1935, Albert Einstein and Nathan Rosen studied a mathematical structure related to solutions of general relativity. Their work showed that, in the mathematics, space-time could be extended in a way that looked like a bridge between two regions. This structure is often described as a wormhole. The image is familiar. Instead of travelling across the surface of an apple, a worm burrows through the middle, taking a shorter route between 2 points. In space-time, the idea is similar in spirit. A wormhole would be a shortcut or connection between separated regions, not by moving faster than light through ordinary space, but by changing the geometry through which the journey happens. It is a beautiful image. It is also one that needs careful handling. The original Einstein-Rosen bridge is not a stable, traversable tunnel for spacecraft, people, signals, or anything else hoping to arrive with its molecules still on speaking terms. It appears in an idealized mathematical extension of a black hole solution, but it does not behave like a practical passage. The bridge closes too quickly. Anything attempting to cross would not make it through. This is where the distinction between mathematical extension and physical travel becomes important. Equations can describe possible structures within a theory. They can reveal that a solution has hidden regions, extended coordinates, or surprising geometry, but that does not automatically mean the structure exists in the real universe as something usable. A mathematical diagram can include regions that are not formed by realistic collapse, or that require impossible conditions, or that vanish before anything can pass through them. General relativity is very good at producing dramatic geometry. The universe, however, is not always generous enough to make that geometry available for tourism. The maximally extended Schwarzschild solution is a good example. The ordinary Schwarzschild black hole describes the space-time around a non-rotating, uncharged black hole. When this solution is extended as far as the mathematics allows, it contains not just one exterior region, but two. These two exterior regions are connected by an Einstein-Rosen bridge. At first glance, that sounds like exactly the kind of escape route imagination wants. Fall into one side, emerge somewhere else. Very convenient. Almost suspiciously convenient. And suspicion is appropriate. The bridge in the maximally extended Schwarzschild solution is not traversable. It pinches off too quickly for light, matter, or information to cross from one exterior region to the other. The moment you try to use it as a tunnel, the geometry refuses to cooperate. It is less like a doorway, and more like a doorway drawn beautifully on a wall that collapses the instant you reach for the handle. There is another issue as well. Ordinary black holes in the universe are expected to form from gravitational collapse, such as the collapse of massive stars or the merger of compact objects. These realistic black holes are not the same as the eternal, perfectly symmetrical black hole described by the maximally extended Schwarzschild solution. The full mathematical extension includes regions that are useful for understanding the theory, but not necessarily produced by real astrophysical formation. So, if a star collapses into a black hole, we do not expect it to create a convenient Einstein-Rosen bridge to another universe. The collapsing matter forms an event horizon, and in the classical picture, future-directed paths inside led inward toward a singularity. There is no confirmed wormhole exit tucked behind the horizon like an emergency door at the back of a theatre. Physicists have still studied the possibility of traversable wormholes. Kip Thorne, Michael Morris, and Ulvi Yurtsever explored wormholes that could, in principle, be crossed. Their work showed that keeping such a wormhole open would require exotic matter or exotic energy conditions, often described as negative energy. Negative energy is not simply ordinary energy with a gloomy attitude. It means energy arranged in a way that violates the usual conditions matter is expected to obey in general relativity. Quantum theory does allow some limited negative energy effects in special circumstances, such as those related to the Casimir effect. But producing enough negative energy in the right configuration to hold open a macroscopic traversable wormhole is far beyond anything known to be physically possible. It is not merely a difficult engineering challenge, like building a larger bridge or a more patient kettle. It may require forms of matter and energy that the universe does not permit on the needed scale. This is why wormholes remain scientifically interesting but physically unconfirmed. They are allowed in some mathematical models. They are useful for exploring the structure of space-time, but they are not known to exist, and ordinary black holes are not expected to be reliable entrances to them. There is also a more modern and subtle connection between wormholes and quantum information. In 2013, Juan Maldacena and Leonard Susskind proposed an idea often expressed as Einstein-Rosen equals Einstein-Podolsky-Rosen. Written in words, it suggests a deep relationship between wormholes and quantum entanglement. The Einstein-Rosen part refers to wormhole-like bridges. The Einstein-Podolsky-Rosen part refers to a famous 1935 argument by Albert Einstein, Boris Podolsky, and Nathan Rosen about quantum entanglement. Entanglement is a quantum connection between systems where the full description of each part cannot be separated cleanly from the other, even when the parts are far apart. The proposal does not mean that ordinary entangled particles are connected by little tunnels that spacecraft could fly through. It is far more theoretical and subtle. The idea is that space-time connections and quantum entanglement may be two sides of a deeper relationship in a theory of quantum gravity. Wormholes may help physicists understand how information is organized in gravitational systems, especially black holes. This is a powerful clue, but it is not an escape route. It does not currently tell us that anything falling into a real black hole travels through a wormhole and emerges elsewhere. It does not turn black holes into portals. It suggests that the mathematics of connection, geometry, and quantum information may be linked at a deeper level than ordinary intuition suggests. So wormholes occupy a strange place in the black hole story. They are not nonsense. They are not merely fantasy. They arise from serious mathematics and general relativity and from serious questions in quantum gravity. But they are also not confirmed physical tunnels, and they do not provide a simple answer to what happens inside a black hole. The temptation is understandable. If the black hole interior leads to a singularity, and if the singularity marks the breakdown of known physics, then the mind looks for another path, a bridge, a hidden exit, a passage through the dark. But the evidence does not currently support that comforting picture for ordinary astrophysical black holes. For now, wormhole-like ideas are best seen as tools for thinking, not as confirmed destinations for falling matter. They may teach us something profound about space-time, entanglement, holography, and the quantum structure of gravity. They may even point toward a future theory in which the interior of a black hole is understood very differently. But they do not yet tell us wherein falling matter goes in the real universe, and because no signal can return from beyond the event horizon, the best evidence we have about black hole interiors still comes indirectly. We study how black holes bend light, move stars, heat gas, merge, ring, and disturb space-time outside themselves. The hidden interior remains sealed away, while the exterior writes clues across the universe in gravity, radiation, and waves. We cannot look directly inside a black hole. That's the first honest limit. The interior lies beyond the event horizon, and once something crosses that boundary, no light, radio signal, particle message, or neatly written field report can return to the outside universe. The inside is hidden not merely because it is dark, distant, or difficult to image, but because the structure of space-time prevents information from escaping. And yet, black holes reveal themselves in many powerful ways. They reveal themselves through gravity, by forcing nearby stars into fast, tight orbits. They reveal themselves through radiation from surrounding matter as gas heats to extreme temperatures before crossing the event horizon. They reveal themselves through the bending of light, producing shadows and distorted rings, and they reveal themselves through gravitational waves, ripples in space-time produced when black holes collide and merge. So although the interior remains sealed away, the outside universe carries clues. One of the clearest examples sits at the centre of the Milky Way. There, hidden behind thick clouds of dust and gas from our viewpoint, lies the compact radio source known as Sagittarius A star. It is associated with a supermassive black hole with about 4 million times the mass of the Sun. We do not know this because we have looked inside it. We know it because of what nearby stars do. For decades, astronomers tracked stars orbiting an unseen object at the centre of the galaxy. One of the most important of these stars is called S2. It follows a long, stretched orbit around Sagittarius A star, coming extremely close to the central object before sweeping away again. By measuring its motion carefully, astronomers could calculate the mass concentrated inside its orbit. The result was astonishing. Millions of solar masses had to be packed into a region small enough that no ordinary cluster of stars, gas, or dark objects could sensibly explain it. The best explanation was a supermassive black hole. Andrea Ghez, Reinhard Genzel, and their research teams played central roles in this work. Their observations of stellar motion near the centre of the Milky Way provided some of the strongest evidence that supermassive black holes are real astrophysical objects. This was recognised with the Nobel Prize in Physics, shared with Roger Penrose, whose theoretical work showed that black hole formation is a robust prediction of general relativity. Another major clue came from the Event Horizon Telescope. The Event Horizon Telescope is not one ordinary telescope. It is a global network of radio observatories linked together to act like an Earth-sized instrument. By combining observations from different locations across the planet, scientists can achieve the extraordinary resolution needed to study the region very close to a supermassive black hole. In 2019, the Event Horizon Telescope collaboration released the first image of the shadow of the black hole in the galaxy Messier 87. Later, it released an image of Sagittarius A star at the centre of the Milky Way. These images were not simple photographs of a black surface. A black hole has no solid surface to photograph. Instead, they showed light from hot material bending around the black hole's intense gravity. The black hole shadow is the dark central region caused by photon capture and extreme gravitational lensing. Photons are particles of light. Near a black hole, some photons can orbit temporarily, while others are swallowed across the event horizon. Light from surrounding plasma is bent, looped, and distorted by curved space-time. The shadow marks the region where light paths are removed from the view of a distant observer. This shadow is not the event horizon itself seen as a material edge. It is larger than the event horizon and shaped by how light travels through the curved space-time around the black hole. Still, it is powerful evidence that the object behaves just as general relativity predicts. It is the universe giving us a silhouette of something that cannot shine. Then there are gravitational waves. In 2015, the Laser Interferometer Gravitational Wave Observatory detected gravitational waves from the merger of two black holes. These waves were tiny stretches and squeezes of space-time itself, produced as two massive compact objects spiraled together, collided, and settled into one larger black hole. The signal had travelled across the universe before passing through Earth and shifting the lengths of the detector arms by far less than the width of a proton. The achievement was extraordinary. The Laser Interferometer Gravitational Wave Observatory confirmed one of the strongest predictions of general relativity in the most direct way yet. Rainer Weiss, Kip Thorne, and Barry Barish were later awarded the Nobel Prize in Physics for their roles in making gravitational wave detection possible. The detectors did not see black holes with light. They heard space-time ring. That ringing matters. When two black holes merge, the final black hole is disturbed, rather like a struck bell. It then settles down into a stable state by emitting gravitational waves. This final settling phase is called ringdown. The pattern of the ringdown depends on the mass and spin of the final black hole. General relativity predicts very specific ringdown behavior for a black hole. By comparing observed gravitational wave signals with those predictions, physicists can test whether the final object really behaves like the black holes described by Einstein's theory. So the evidence comes from several directions at once. Stars orbit unseen compact masses. Hot plasma shines before crossing the horizon. Light bends into shadows and rings. Black holes merge and produce gravitational waves with the predicted in spiral merger and ringdown patterns. Each line of evidence is different, but they point toward the same conclusion. Black holes are real. Still, there is a boundary to what these observations can tell us. They do not show the inside. The orbit of S2 tells us about the gravitational field around Sagittarius A star. The Event Horizon Telescope images reveal the near-horizon region through bent light and glowing plasma. Gravitational waves reveal how compact objects merge and settle, but none of these observations sends a message out from behind the event horizon. The interior remains inferred, not seen. That does not make it imaginary. Much of science works by inference. We know Earth's deep core through seismic waves, not by visiting it. We know the interiors of stars through light, neutrinos and models of nuclear fusion, not by scooping out a handful of solar material. In the case of black holes, the inference is more extreme because the horizon blocks direct communication. But the outside behavior is so consistent, so mathematically structured, and so well matched to general relativity that black holes have become part of mainstream astrophysics. What the observations support is the existence of extremely compact objects behaving as black holes, with event horizons or something extraordinarily close to them. What they do not yet reveal is the final inward fate of matter and energy after the horizon is crossed. For that, physicists must use theory. They must follow general relativity inward. They must ask where quantum mechanics becomes important. They must study singularities, horizons, entropy, radiation, and information. And because direct observation stops at the horizon, the final fate of falling matter remains one of the deepest questions hidden inside the dark. What happens inside a black hole? In the classical picture, the answer is stark. Anything that crosses the event horizon of a simple black hole continues inward toward the singularity. Not because it has made a bad turn, not because the black hole keeps pulling harder in the ordinary sense, but because, once inside the horizon, every future directed path leads deeper in. The singularity is not a place that can be avoided by steering carefully around it. In a simple, non-rotating black hole, described by general relativity, it lies in the future of anything that falls through the horizon, as unavoidable as the next moment. This is the clean answer from classical general relativity. It is also the place where the clean answer begins to break. As matter falls inward, it is stretched and compressed by tidal forces. The direction toward the centre is stretched, while the sideways directions are squeezed. If the black hole is small, those tidal forces may become destructive before the event horizon is crossed. If the black hole is supermassive, the horizon may be crossed calmly, but deeper inside the same fate eventually arrives. The difference is not whether the tidal forces appear, but when they become impossible to survive. Ordinary matter is not built for such conditions. A falling object would not remain a recognizable object all the way down. A spacecraft would be pulled apart. A planet would be distorted and disrupted. A star would be stretched into streams of plasma. Matter would be heated, compressed, separated, and driven into conditions far beyond anything familiar from laboratories or ordinary astrophysics. Atoms would not remain atoms in the usual sense. Atomic structure depends on electrons arranged around nuclei, held by electromagnetism and described by quantum mechanics. Under the extreme curvature and energy density expected deep inside a black hole, the familiar organization of electrons, nuclei, and chemical bonds would be destroyed. Nuclei themselves would not remain ordinary nuclei forever. Protons and neutrons are held together inside atomic nuclei by the strong nuclear interaction, but even they are not indestructible little beads. They are made of quarks and gluons, described by quantum chromodynamics. Under sufficiently extreme conditions, the ordinary distinctions between atoms, nuclei, protons, neutrons, radiation, and other particle states may cease to be meaningful in the way they are outside the black hole. This does not mean physicists can describe every stage with confidence. It means the opposite. Classical general relativity tells us that matter is driven toward a region where curvature grows without limit, but it does not provide a complete quantum description of what matter becomes there. At the deepest point, known physics stops being able to give a final physical account. From the outside, however, the black hole does still keep some accounts. If an object falls in, its mass and energy increase the mass of the black hole. If it carries angular momentum, it can change the black hole's spin. If it carries electric charge, it can in principle change the black hole's charge, although real astrophysical black holes are expected to remain nearly neutral overall because they attract opposite charges from their surroundings. These are not minor details. Mass, angular momentum, and charge are the main properties by which an external observer can describe a settled black hole. What disappears from outside view is the object's detailed structure. A falling object might be a star, a gas cloud, a planet, a book, a piano, or a sandwich with a surprisingly complicated emotional history. Before crossing the horizon, these objects differ enormously in shape, composition, temperature, texture, and microscopic arrangement. After crossing, the outside universe can no longer observe those details directly. The black hole eventually settles into a state described only by a few measurable quantities. This is the no-hair idea. Black holes have no hair, in the phrase associated with John Archibald Wheeler. The phrase means that from the outside, a black hole does not preserve visible details about the material that formed it or fell into it. It has mass, it may have spin, it may have electric charge, but it does not display the rich, messy history of everything it has swallowed. This simplicity is powerful, but also troubling. Physics usually depends on predictability. If the full state of a system is known, the laws of physics should tell us how it changes. Black holes seem to hide many details behind a horizon, and then classical general relativity points inward toward a singularity where prediction itself breaks down. Roger Penrose proposed the idea of cosmic censorship as a way of preserving predictability in the wider universe. Cosmic censorship is the conjecture that singularities formed by realistic gravitational collapse are hidden behind event horizons. In other words, nature may allow singularities in the mathematics, but it keeps them covered. The event horizon acts like a boundary that prevents the singularity from directly affecting distant observers. A singularity hidden behind an event horizon is disturbing, but it is at least sealed away. A naked singularity would be different. A naked singularity would be a singularity visible from outside, not hidden behind a horizon. Such an object could, in principle, expose the breakdown of classical physics to the wider universe and make prediction deeply uncertain. Cosmic censorship suggests that gravitational collapse normally prevents this by clothing the singularity with an event horizon. But cosmic censorship is a conjecture, not a complete final answer. And even if singularities are hidden, hiding the problem is not the same as solving it. Deep inside the black hole, the fate of matter remains one of the places where a complete theory of quantum gravity is most urgently needed. General relativity gives the inward road. Quantum mechanics must eventually explain what happens when that road reaches the smallest and most extreme scales. Until those two descriptions are fully joined, the final fate of anything that falls in remains partly known and partly hidden. And the story may not end there. Black holes may not last forever. If Hawking radiation is correct, they can slowly lose energy across immense timescales. So the long-term future of the interior cannot be separated from the long-term future of the black hole itself. The question becomes not only what falls inward, but what happens if the black hole eventually evaporates away? Black holes may seem permanent, as if they are the universe's final storage boxes. Matter falls in, light cannot escape, and the event horizon closes behind everything with a silence that feels absolute. But according to modern physics, even black holes may not last forever. The reason is Hawking radiation. Stephen Hawking showed in 1974 that when quantum fields are studied in the curved spacetime around a black hole, the black hole should not be perfectly black. It should emit a faint thermal radiation. This does not mean that ordinary light is escaping from inside the event horizon. Nothing inside the horizon sends a signal back out in the usual way. Hawking radiation is a quantum effect connected to the behavior of fields near the horizon, as seen by distant observers. The result is astonishing. A black hole can slowly lose energy. And because energy and mass are connected, losing energy means losing mass. Over immense spans of time, a black hole can shrink. It can grow hotter as it shrinks. And, at least in the standard theoretical picture, it may eventually evaporate. This is one of those ideas that is both dramatic and extremely patient. For large black holes in the current universe, Hawking radiation is far too weak to matter in any practical astrophysical sense. A black hole with the mass of the Sun would have a temperature far below the cosmic microwave background, the faint radiation left over from the early universe. The universe around it is warmer than the black hole's own Hawking temperature, so such a black hole absorbs more energy from its surroundings than it loses through Hawking radiation. In other words, if a solar mass black hole is disappearing, it is doing so with the sort of leisurely attitude that makes glaciers look impatient. The evaporation time for a black hole with the mass of the Sun is vastly longer than the present age of the universe. The universe is about 13.8 billion years old. A solar mass black hole would take something like 10 to the 67 years to evaporate by Hawking radiation, assuming it was isolated and not feeding on surrounding matter or radiation. That is not merely a long time. It is a time so long that ordinary cosmic history becomes a tiny opening note. Supermassive black holes last even longer. Because larger black holes are colder and radiate more weakly, a black hole with millions or billions of solar masses would survive for absurdly greater timescales. The supermassive black holes at the centres of galaxies are not close to evaporating. They are still part of the present cosmic architecture, shaping stars, gas, and galactic evolution. Smaller black holes behave differently. Hawking temperature increases as black hole mass decreases. This means smaller black holes are hotter. They radiate more strongly. As they lose mass, they become hotter still, which makes them radiate faster. The process accelerates as the black hole shrinks. This leads to a possible final phase in which a very small black hole might release a burst of high-energy radiation. But this final stage is also where our confidence becomes more careful, because it would involve extremely high curvature, very small scales, and perhaps particle physics beyond what is currently known. This is one reason scientists have long been interested in primordial black holes. Primordial black holes are hypothetical black holes that may have formed in the early universe, not from collapsing stars, but from unusually dense regions in the hot young cosmos. In the early universe, matter and radiation were packed far more densely than they are today. If some region had a large enough density fluctuation, gravity might have compressed it into a black hole directly. This idea has been studied by researchers, including Stephen Hawking and Bernard Kerr. Primordial black holes could, in principle, have a wide range of masses. Some might have been enormous, others might have been tiny. The smallest ones, if they ever existed, could have evaporated long ago. Others with particular masses might still exist today, and have been considered as possible contributors to dark matter, although no confirmed population of primordial black holes has been found. The possibility matters because tiny black holes would evaporate much faster than stellar or supermassive black holes. A black hole small enough could have a lifetime comparable to the current age of the universe. If such objects existed, their final evaporation might produce high-energy particles or gamma rays. Astronomers have searched for signs of this, but so far there is no definitive detection of evaporating primordial black holes. The final evaporation stage remains deeply uncertain. Hawking's calculation is powerful, but it is usually performed using quantum field theory on a curved spacetime background. That means the black hole's gravity is treated classically, while the fields around it are treated quantum mechanically. This is not a full theory of quantum gravity. As a black hole shrinks toward extremely small size, that approximation becomes less trustworthy. Near the end, the black hole could approach scales where space-time curvature is enormous, and quantum gravitational effects cannot be ignored. The Planck length, the Planck time, and the Planck mass become relevant as markers of where our familiar descriptions may fail. At that point, a complete theory of quantum gravity would be needed to say with confidence what happens. Several possible endings have been discussed. One possibility is complete evaporation with information recovery. In this view, the black hole eventually disappears, but the information about everything that fell in is not destroyed. Instead, it is somehow encoded in subtle correlations within Hawking radiation. This fits the modern leaning that quantum mechanics remains unitary, meaning the full information in a closed system is preserved. Another possibility is a long-lived remnant. A remnant would be a tiny leftover object, perhaps near the Planck scale, that stores the information rather than disappearing completely. This idea has attractions because it avoids total disappearance, but it also raises difficult questions. If remnants can store arbitrarily large amounts of information, they may create serious problems for quantum theory and particle physics. A third possibility is that the final stage is resolved by a more exotic quantum gravitational process. The singularity might be replaced. The interior might transition into a new phase. Space-time itself might cease to be described by smooth geometry. String theory, loop quantum gravity, holography, and other approaches have all suggested different ways the classical picture might be incomplete, but none has yet provided a confirmed final answer for real black holes in our universe. This brings the information paradox into sharper focus. If a black hole simply existed forever, one might say the information remains hidden inside, unreachable, but not destroyed. But if the black hole evaporates completely, the hidden interior seems to vanish from the universe. The question then becomes unavoidable. Did the information escape in the radiation? Was it stored in a remnant? Was the classical idea of an interior wrong from the beginning? Or does quantum gravity change the entire question? Black hole evaporation therefore turns the inside of a black hole into a story with a possible ending. Not an ending we can watch for ordinary astrophysical black holes today, and not one fully understood by current theory, but an ending that exposes the deepest tension in modern physics. For now, the honest answer must keep its layers separate. Hawking radiation is a strong theoretical prediction. Large black holes evaporate so slowly that the effect is negligible in the present universe. Small hypothetical black holes would evaporate faster. The final stage almost certainly requires quantum gravity, and the fate of information remains one of the central clues that our understanding is incomplete. So black holes may not be eternal tombs. They may be temporary, though temporary on timescales almost beyond imagination. They may slowly fade, warm as they shrink, and approach an ending where space-time, quantum fields, and information must be understood together. To ask what happens inside a black hole is therefore also to ask what remains when the black hole itself is gone. And the most careful answer is not a single sentence. It is a separation between what is known, what is strongly predicted, and what still lies beyond the edge of current physics. What happens inside a black hole? The most careful answer is that, according to classical general relativity, every future path leads inward. Once something crosses the event horizon of a simple black hole, it does not merely become difficult to escape. Escape is no longer one of the available futures. Light cannot turn around. Matter cannot send a signal back. A rocket cannot choose a clever route home. Every future-directed path leads toward a region where space-time curvature becomes extreme, and where the theory of general relativity eventually stops giving physically meaningful answers. That is the classical answer. It is powerful, precise, and incomplete. The strongest part of the picture begins with Albert Einstein's general theory of relativity. Gravity is not simply a force pulling objects through space. It is the curvature of space-time caused by mass and energy. In the simplest black hole described by Carl Schwarzschild, that curvature becomes so severe that an event horizon forms. The event horizon is not a wall, a surface, or a glowing shell. It is a causal boundary. Beyond it, no event can send light, matter, or information back to the outside universe. For a very large black hole, crossing that boundary may not feel dramatic. A freely falling observer follows a geodesic, the natural path through curved space-time. If the black hole is supermassive, the tidal forces at the horizon may be gentle enough that the observer's local physics seems ordinary for a while. A clock keeps ticking. A small object nearby keeps drifting. There is no special bump at the horizon, no crack in the air, no helpful cosmic sign saying that the return journey has been cancelled. But the lack of local drama does not make the horizon harmless. It means the change is deeper than sensation. The future has been rearranged. Outside the horizon, paths can still lead away. Inside it, all future-directed paths lead deeper inward. Even light, moving at the cosmic speed limit, cannot choose a future that increases its distance from the black hole. The event horizon is the place where outward escape disappears from the structure of space-time itself. Deeper inside, tidal forces eventually become destructive. These are differences in gravitational effect across an extended object. Matter is stretched along the inward direction and squeezed from the sides. In a stellar mass black hole, this spaghettification could happen before the horizon is reached. In a supermassive black hole, it may happen much later. Either way, ordinary structures cannot remain ordinary forever. Spacecraft, planets, atoms, nuclei, and familiar particle arrangements are pushed into conditions where our usual descriptions begin to fail. The deepest classical prediction is the singularity. Roger Penrose's singularity theorem showed that singularities are not merely accidents of perfectly neat mathematics. Under broad conditions, gravitational collapse in general relativity leads to paths through space-time that cannot be continued. In a simple black hole, the singularity is not best imagined as a tiny hard object sitting at the centre. It is better understood as a warning that the theory has reached its limit. When physics produces infinity, it often means the map has carried us as far as it can. Real black holes are also expected to spin, which brings in the Kerr black hole. Roy Kerr's rotating solution is more realistic than the non-rotating Schwarzschild picture. A Kerr black hole twists space-time through frame dragging, creates an ergosphere outside the horizon, and has a more complicated ideal interior. But those inner structures may be unstable, and real black holes are disturbed by matter, radiation, magnetic fields, and gravitational waves. Then the story becomes quantum. Jacob Bekenstein proposed that black holes have entropy proportional to the area of the event horizon. Stephen Hawking showed that black holes should emit Hawking radiation when quantum fields are considered near the horizon. These ideas link black holes to thermodynamics, quantum theory, and information in a way no ordinary star or planet does, and that creates the information paradox. Quantum mechanics says information should not be fundamentally destroyed. General relativity seems to hide information behind the event horizon. If Hawking radiation slowly evaporates the black hole, the question becomes sharper. Where does the information go? The holographic principle, associated with Gerard 't Hooft and Leonard Susskind, suggests that information inside a region may be encoded on its boundary. Other quantum gravity proposals, including string theory, loop quantum gravity, firewalls, fuzzballs, and black hole complementarity, suggest that the classical interior may not be the final story. Some preserve a smooth horizon, some replace it with quantum structure, some change what different observers can consistently say. None has yet been confirmed as the final answer for real black holes, so the safest scientific answer is layered. Outside near the event horizon, modern physics is extremely powerful. Black holes are real gravitational objects, not cosmic vacuum cleaners or magical holes in space. We see their effects in orbiting stars, glowing accretion disks, black hole shadows, and gravitational waves. Deep inside, near the predicted singularity, current theory becomes incomplete. That is what we can say and what we cannot. The inside of a black hole is not merely hidden by darkness, it is hidden by causality itself. No signal can return, so the interior is sealed away by the deepest rules of cause and effect. Black holes quietly show us that our best theories are extraordinary, but not finished. The mystery is not ignorance. It is a map of the frontier pointing to the place where the next understanding has to begin. What happens inside a black hole is partly known through general relativity and partly hidden behind the unfinished boundary between gravity and quantum mechanics. That is the honest answer, and it is more interesting than pretending certainty where certainty does not yet exist. Black holes show us exactly where the universe resists simple explanation. They are not empty gaps in space, or cosmic vacuum cleaners roaming around looking for stars to bother. They are physical regions where matter, energy, space-time, thermodynamics, and quantum theory meet under the most extreme conditions known. The journey begins with Newtonian gravity, where gravity behaves like a force between masses. Then Einstein's general relativity changes the picture, turning gravity into the curvature of space-time itself. Schwarzschild's event horizon gives us the point of no return. Freely falling observers show us that crossing a large black hole's horizon may happen without local drama. Tidal forces reveal how matter is stretched and squeezed. Inside the horizon, all future paths point inward. Then the picture deepens. Singularities suggest that classical general relativity reaches its limit. Kerr black holes remind us that real black holes spin. Accretion disks show how matter outside the horizon can glow with enormous energy. Bekenstein entropy and Hawking radiation connect black holes to thermodynamics and quantum theory. The information paradox asks whether the universe can truly lose information. Firewalls, fuzzballs, wormholes, and other proposals show how strange the interior may become when quantum mechanics is taken seriously. Observations keep the story grounded. The Event Horizon Telescope has imaged black hole shadows. Gravitational wave astronomy has detected black holes merging. Black hole evaporation remains far too slow to matter for large black holes today, but it tells us that even these objects may have endings. Anything crossing the event horizon cannot return, yet it still reshapes the black hole's mass, spin, charge, horizon area, entropy, and future. The singularity is best understood not as a fully known physical object, but as a sign that our current theory has reached its edge. Future progress may come from gravitational wave astronomy, sharper event horizon, telescope observations, quantum information theory, string theory, loop quantum gravity, or a theory not yet imagined. Black holes are dark not because nothing happens inside them, but because what happens there is sealed away from the rest of the universe by the deepest rules of cause and effect.